This paper was presented at the JCT Traffic Signal Symposium 2024, thanks to our media partner Highways News, and sponsored by AGD Systems, Four-Way Consulting, Traffic Group Signals, Smart Micro UK, TRL Software, PTV Group, Census Networks, and Starling Technologies.
Hello, everyone. Sorry for the really long title. I should have just stuck with this. So I'm going to try and just talk you briefly through a method that we started using in Manchester to just slightly improve how we model demand-dependent pedestrian stages, particularly in kind of the early stage scheme appraisals process. So we typically model schemes in LinSig when we're looking at sort of localized junctions as part of that early stage process, and we're using that model to try and just forecast how those proposed changes might impact the junction. With loads of people here doing exactly the same thing. And the results of that initial modelling process will form part of the basis on which we might approve or reject schemes, and also how we might carry those forward. And hence it's pretty critical that that modelling process reflects or predicts reality as accurately as it can. And one of the key challenges in those early stage models is what do you do with demand-dependent stages, especially if it's a stage that isn't yet there, so you don't know how frequently it's going to appear. So in Manchester, we're currently working to upgrade loads of our existing junctions that currently don't have any pedestrian facilities to just include new pedestrian crossing facilities. And often as part of that, we're adding a new all-red pedestrian stage, which becomes demand dependent. And that stage, naturally, when we're designing it, we don't know how often it's going to appear. And so that's kind of what this process is trying to just improve slightly how we deal with that stage. Traditionally, we would either have modeled that stage simply as appearing in every cycle. The benefit of that, it's conservative, so you can defend that when you're doing your appraisals process, but the drawback, of course, is that because it's conservative, it's going to give you the worst results in terms of junction efficiency. The other kind of traditional approach would be to model it as appearing every other cycle. That's going to give you better results in terms of efficiency, but it can be quite hard to defend if you're not basing that on any data, so it becomes quite difficult to use that in your appraisals process. So effectively what I'm looking at is saying, well, if we have pedestrian count data at those locations as part of our scheme process, then we can use that data to try and predict that appearance frequency. And there's lots of different ways that demand-dependent stages are dealt with in different software packages. This is very much looking at early stage scheme appraisal and very much focused on LinSig. And it's all based on some fairly well-established maths. Now, I apologise, nobody really wants maths at 2:30 on a Thursday afternoon, so we'll try and make it quick. But there's a probability function known as the Poisson distribution, and we can effectively use that to convert our pedestrian count data into a predicted appearance frequency. The distribution allows us to calculate the number of events that are likely to occur in a set time period based on the average rate of those events occurring. So for us, we're interested in the arrival of pedestrians at a signalised crossing, and the kind of average rate is given by our count data. So before we go into the actual equation, just briefly, there's a couple of assumptions that are sort of inherent within a Poisson distribution, kind of three that I want to highlight within this scenario. The first of which is that every pedestrian has to arrive on their own, so you're not getting any people walking in groups. The second assumption would be that every pedestrian places a demand, so you've not got anyone crossing without first pressing the button, and you also have no curbsides to cancel down demands. And then the final assumption is that the arrival of any one pedestrian isn't linked to the arrival of the previous pedestrian, so you've not got a sudden spike due to the arrival of a bus or something. Now, you're all sat here going, well, none of that's true, and obviously you're right, that doesn't hold in most scenarios. But the way in which those assumptions fail leads to the equation giving us conservative results. So if you've got people walking in groups, as far as the appearance frequency is concerned, you could consider that as one person. You don't need to count them as individuals. So the fact that we are counting them as individuals means we're going to overestimate. And similarly, if someone doesn't place a demand, well, you could just ignore them in reality. And by not doing that, again, you're being conservative. So we are going to be overestimating the appearance frequency. But that's, again, kind of what we want, in the sense that then we can defend that we're not being sort of overly optimistic in the results from that modelling exercise. So, right, I will go through this quickly and then we'll move on from the maths, I promise. So we want the probability of the pedestrian stage appearing. That's the same as the probability of at least one pedestrian arriving within the window for which we're accepting demands. And that's the same as 1 minus the probability of no pedestrians arriving. So if we then use the equation from a couple of slides ago, you can factor that down, and you get the probability of the pedestrian stage appearing being 1 minus the exponential of minus lambda, where lambda is just defined as the expected number of pedestrians arriving within that time period that you accept demands for. So you can calculate that if you've got account data, divide that by the time period to get the average rate of pedestrians, and multiply that by the time period for which you accept demands. So your cycle time minus the length of that pedestrian stage, including the intergreen. And then the final thing to realize is you need to iterate that equation, because the time period that I've just talked about only holds if the pedestrian stage does appear. But if you've got a cycle where the pedestrian stage does not appear, you're going to accept demands for that whole time period. So you factor down that time period by your probability, repeat the equation a couple of times, and it converges pretty quickly on an answer. But I promise that's the maths done. So what I'm going to show you is what we've done is we've taken existing sites in Manchester that already have an all-red demand-dependent pedestrian stage. They also all have pedestrian count data that's recent, and we have an appearance frequency data for the same time period from our UTC system. And I'm going to compare the actual appearance frequency with what we would have predicted using this equation. The sites are kind of spaced around Greater Manchester, and we looked at quite a lot. In the paper, I've only presented 5 of those as sort of a summary of the sites, and I'm actually only going to do 4 here, just because it's easier to do 4 on one slide. And it's just worth highlighting that we've avoided sites with a really high pedestrian demand because the results are uninteresting, because your stage is just going to appear every cycle. And we've also avoided sites with really low demands where the stage hardly ever appears. So this is kind of a summary of those initial results. So you've got the 4 sites plotted there. You've got the probability of the pedestrian stage appearing in any given cycle on your y-axis. And you've got time of day on the x-axis. And the last 2 sites, we only had data for the afternoon, hence why it's sort of only half a plot. And then on each plot, you've got the actual probability of the stage appearing in any given cycle based on recorded UTC data in the black. And in the yellow, you've got the appearance probability, or the predicted probability that you would have got using the Gaussian equation, the Poisson equation that I showed you a couple of slides ago. It's worth pointing out the data points are all a bucket of time. It's not an instance in time, it's an hour centered around that point in time. Because it's an average equation, it relies on taking averages, so you can't do it for an instance in time, but you can over a time period. And I think there's kind of 3 sort of initial observations from these graphs. The first is just that the shape of that predicted profile matches the actual pretty well. Probably an expected result, because of course the appearance frequency is based on how many pedestrians you have, but it's reassuring that the shapes match. And the second observation is I said that the way in which the assumptions break down leads to it being conservative. And again, this is backed up by the data here, where you can see that we're always overestimating the appearance frequency of that pedestrian stage. So the predicted is always above the actual. And then the final observation is that you'll notice the level of that overprediction varies quite substantially. That's due to a whole host of factors, and it can be really quite a substantial overprediction. So we are still significantly overestimating how frequently that stage occurs, but we are going to see improvements over just modeling it as appearing in every cycle. And I'll show you that in some modeling results in a second. So very briefly, I'm not trying to give you a tutorial on how to do bonus screens, but the way we've applied this predicted frequency is using bonus screens in LinSig. And effectively, if you're modeling a stage, if you do a normal cycle with the pedestrian stage appearing, you can calculate how much time is lost to traffic. And then you can do the same again in a cycle where the pedestrian stage doesn't appear. And the difference between those two is effectively your additional lost time due to that pedestrian stage appearing. And if you factor that by your predicted appearance frequency, then you're left with a representative lost time. And then you can use that to calculate bonus screens that you would apply to the relevant lanes. And then you can run your LinSig model with the stage appearing in every cycle, but using bonus screens to simulate the effect of it only appearing every, well, whatever percent it was, 74, 62, whatever it is. So what I've done is, for the sites that we saw the graphs for, I've then modeled those in LinSig using this approach. On here, I've got the PRC values, practical reserve capacity. It's not the only value I could have chosen, but it was just one that gives an indication of the differences that you might see. And so the first thing I've done is I've just compared modeling it as every other cycle with modeling it as every cycle, just to demonstrate that the difference in those PRC values can be really substantial. So the approach that you take to modeling those demand-dependent stages can have a really significant impact on how good your appraisal is going to look. And then in that third column, you've got the kind of PRC results that you get when using the bonus screens based on the probability that we've estimated using that Poisson distribution. And as you can see, it is giving us improvements over doing it just every cycle, and quite substantial improvements, But that level of improvement, like I say, it varies significantly depending on how frequently you estimate your pedestrian stage to be appearing. But it gives you the potential to gain quite substantial efficiency improvements when you're doing that sort of scheme or scheme appraisals process and you're using these models as part of that process. I think, yeah, that was quick, wasn't it? So hopefully I've gone through a sort of a conservative approach that uses probability equations to estimate an appearance frequency for a new pedestrian stage. I know I've done it on existing sites to show kind of how it would work, but we've then been using that for new schemes as part of this appraisals process. And hopefully I've shown that that process can lead to significant improvements in your results when it comes to the efficiency of your modelling or the reported junction efficiency. And then that allows us to use that in the appraisals process and hopefully make it a bit easier to gain those approvals. I did want to point out there's one really key caveat perhaps, which is if you're looking at new pedestrian facilities, I haven't accounted for drawn demand at all. But if you're putting in a new pedestrian facilities, you're probably expecting to draw new pedestrians themselves. So I haven't accounted for that in here. But it depends how you account for that in your appraisals process. And as long as the two tally up, you're okay. So if you're in your appraisals process, you're going to use your ped count to do some sort of benefit analysis. If you growth that ped count for that process, then you can growth it for this process. And if you're not growthing it for that process, then you probably shouldn't be growthing it for this process either. The two is trying to be as like for like a comparison as possible. And then the other thing was, but I mean, its potential next step perhaps is to try and quantify some growth factors. There may well already be research out there that does this, however. And then the other next step that I wanted to highlight is just that the way in which those assumptions fall down that I talked about at the beginning with the people walking in groups and also the people crossing on red, not placing a demand. If it were possible to quantify those two factors, you might be able to further improve the accuracy of this technique. But I think that's going to be very, very difficult. And I expect those factors vary massively depending on all sorts of factors and site-specific sort of location factors, etc. But even without doing that, hopefully I've shown that there's some efficiency improvements to be gained from doing this. So there we go. I think that's me. Thank you.
Right then, have we got any questions from the audience? We go for a microphone over here first, please.
Hi, it's Richard Bishop, SLR. Strikes me, well, I've used this in the past. That approach can also be used for things like any stage that's going to detract from capacity. So, for instance, a separately signalled right turn. Yeah. So, I'll just throw an example in there. You've got 60 vehicles calling a demand-dependent stage, 60-second cycle. You don't expect, like your pedestrian examples, you don't expect all of them to turn up. You don't expect 60 cycles. It'd be demanded 60 cycles in the hour.
Yeah.
I just worked it out. I think the Poisson distribution is about 63% of the time. So you can take your approach, which I think is a really good approach, and you can use that for other things as well to try and get a more realistic analysis of what's going on.
Yeah, thank you. Yeah.
Any further questions from the audience? Multiple ones coming from the... Hang on, you wait for the mic.
It's not a question, but if you go back in the past, Transport for London commissioned behaviour study on pedestrian crossings in London. It's a really good document that you'll be able to ask TfL to get hold of. And it just basically went into researching lots of sites of London, but then gave the arrival time and when people cross before green, after green, during green. So it would just give some more robust measures, I think, to what you've been doing. So that's all. Just if you're interested, it should be a good read. I didn't write it, so it's a good read.
Perfect, thank you. I'll have a look into that.
Hello, Mr. Playdell.
Thanks, Tom. Tobias, nice. I think it was sort of echoed up there with the right turners, but advanced stop lines for cycles. This would feel like it would lend itself to being used to determine how often advanced cycle demand stages were called. Reasonable?
Yeah, I think so. Yeah, if you had a cycle count and you had an early release, I don't see why not, yeah.
So if I can extend that idea, there's a difference between natural platooning behaviour, where you probably can't use this, and situations where each arrival is truly free to move. Is that a fair assessment?
Yeah, I think if you've got really strong platooning, you absolutely can't be doing this. But if you're approaching something that's roughly sort of normal distribution-wise, then I think you're probably okay.
Yeah. Thank you.
Okay, have we got any other audience questions? Otherwise, I'm going to put one in quickly.
Yeah.
Sorry,
I thought
you got away with
it.
it. The use of this technique is obviously giving you some slightly different results in the modelling. Has it actually led to any changes in the design of sites to actually maybe be able to say, well, it's performing better, we don't need as many lanes for motor vehicles or something?
Interesting. I don't think it's probably because it's still quite new, we've probably not actually got to the point yet where any scheme has gone all the way through to kind of being, if you like, ready for construction. So I don't know of anywhere that has yet had that impact. Hopefully it will. Yeah.
Okay, thank you. There's nothing else. If you'd like to show your appreciation.
Thank you.